No. Oh, I lost. Oh, I lost your audio again. I don't know why. I still can't hear you. Let's see. No, nothing for me. I don't know if everybody else can hear you. You can, all right. Right. But guys, can you hear me at least? Just to make sure the audio is working. All right. Maybe a loose connection or something, I don't know.
Can you hear me?
Yeah, now I can.
Yeah, I changed to my laptop microphone. Oh dang. I'm really sorry. This is the first time this happened, but uh,
No worries.
I'll restart the intro. So uh, hi everyone. I'm really excited to interview and host Dr. Wassim Jabi. He's currently course director of MSc Computational Methods in Architecture at Cardiff University. I got to know about Professor Wasim from CMOUD 2020 conference, where it was my first time to attend that conference, and I was observing all the amazing discussions happening at that time. And then after that, I started following Dr. Wasim's work on Twitter and other platform, and I saw amazing development. And it's very rare, and I this might be like I think you are the first professor I have seen who's doing like software development from scratch. So it's very inspiring to see people in our industry taking up that challenging role. And I could only imagine how much difficulty it would have been to do everything from scratch, do fundraising, and maybe that's some discussion which will I'll definitely would like to know the origin of the topology and the how the idea was planted. And but this is a huge inspiration to a lot of architecture technologists like me who are interested to do software development, and we see work like this, and it gives a good hope to us to develop some amazing tools like this. So thanks a lot for your time to do this, and I'm very excited.
Great, thank you for having me and inviting me to give this talk. So I'll just jump in then, if you don't mind, and tell you a little bit about Topologic and where it came from. And I'll try in this presentation to show something a little bit different than what I've done in previous. I've been interviewed before and given some webinars, etc. So I'm hoping at least to update people on some new developments with Topologic. But always, as always, there are people who have not seen Topologic before, so they need to understand where it came from, what it is about, what's the name about, etc. And how is it? Why is it interesting? Why is it different? So first of all, I always start with this slide to acknowledge that Topologic is not the result of only one person's work. It is a whole team, and the original concept or the original kind of interest in non-manifold topology actually came from Professor Robert Aish, who is now a visiting professor at UCL in London. And if you know Professor Aish, he was with working on general components, and then worked on design script at Autodesk, and then left Autodesk, became a professor at UCL. And that's where I met him at a workshop where he was doing a workshop on design script. And in that workshop, he took some time at the end to show something called non-manifold topology. And I'll explain what non-manifold topology is in a second. At that time, I was writing software that connected modeling in 3D Studio Max to OpenStudio to do energy analysis. And I got intrigued because I saw that non-manifold topology matches building engineering, building energy models, BIM models. So I thought that would be fantastic. So if we can combine the two. So I started using design script. At that time, it was connected, I think, to AutoCAD, and wrote the glue software to make sure that we can create a building as a simple energy model, move it to OpenStudio, do the analysis, get the colors and the values back, and display them back in 3D Studio Max. And it worked really, really fantastically well. And then we started hearing the news about design script being incorporated in Dynamo, and I was like, oh, exciting, so Dynamo is kind of the new Grasshopper, and it would be really fantastic to do that. So I started having discussions with the Dynamo team about including non-manifold topology, which is a feature in ASM, in the shape modeler, which is the basis of a lot of the software from Autodesk. It is embedded in there. They have it. It's in there. But unfortunately, for technical reasons, they couldn't include it in Dynamo. So they took away that capability. And so I've kind of reached a dead end with that, and I needed to do my research. So I went back to Robert Aish, who by that time had left Autodesk. And as I said, he was a professor at UCL. And I told him, how about we write a proposal, a grant, and get funded to do it the way we wanted to do it. All respect to Autodesk, but I thought we have our own ideas about how we would like to do it at a larger scale. And that's what we proposed. So he and I sat down and wrote the proposal. We were joined by Dr. Simon Lennon a bit later, and we proposed it to the Leverhulme Trust for a 3-year project, £300,000 to create this thing called enhancing the representation of space in building information modeling, basically. And thankfully, they agreed with us. They thought it was very interesting, and they funded it. So we hired Katerina, and we hired Nicholas, who came to us from computer science. He's a programmer, and he's the main programmer of the software, of the original C++ code base. He's the main programmer of that. So we took 3 years to develop it, so it was quite a long time, and we developed it first for Dynamo, and then we moved it to Grasshopper. So now it's running on both, and then after the project ended, with some help, I converted it or wrapped it into a Python kind of envelope so that it's available as a Python module, and now we're doing a second rewrite on it. Because we're not happy with the first attempt, so we're going to rewrite it. So we moved it to an open source, completely an open source code base. It's never going to be for sale. It's never going to be, we're never going to charge anybody. It's always free and open source, and that's near and dear to our hearts. And it runs now on. We have it proof of concept running on Windows, on Mac, on Linux. So it runs on these 3 platforms. So let's kind of start from the beginning, basically. What is this term non-manifold geometry and manifold geometry? So let me try to explain that as best as I can. First of all, I want to tell you that manifold and non-manifold are a bit of the wrong terms. The real mathematical terms for it is either 2 manifold or 3 manifold or 4, 5, 6, n manifolds, so more than 2. So why is the number important? When we talk about 2 manifolds, we're basically talking about an entity, like a point in space, that divides the overall universe into 2 entities or 2 manifolds. Either you are on the outside of that point, that's the world, as you can see here, manifold number 1 is on the outside world, or you're inside that space, inside that solid, so that's manifold number 2. So that's called a 2 manifold, which means it's called manifold. Most of our CAD systems that we use today use manifold geometry. And if we have a non-manifold condition, it's considered a mistake. So what is non-manifold? Non-manifold, let's start with 3 manifolds, is when a point in space does not obey the rule that I just told you about. That means a point in space can divide the world into 3 manifolds. There is one manifold is the outside world, but then there is another manifold, which is the interior of one cell, one cube, one solid, and there is another manifold, which is also another cube or another cell or another region of some sort. So if you look at this red dot on the right side, it sits right at the intersection of these three worlds. And it might sit at the intersection of 1,000 worlds. So in that case, that point in space is called a non-manifold point. What does this mean? What does this mean practically is that you can have enclosures of space that have interior subdivisions, right? All expressed as one entity. So when you look at these, I know they're hand-drawn sketches. I thought that would be nice to do that, but we are not talking about a grouping of objects in space. Those would still be manifolds, and you would have two vertices and two edges at that point. We're talking about a single vertex and a single edge that is separating those entities, or a single face that separates those entities. And that's where you start having objects that have interior partitions in them, or non-manifold edges. So if you look at something like that, this is called a tesseract. This is not topologic, but just an animation I found online. We did an example of it. You'll notice that there are interior subdivisions, there are interior faces, interior lines. And what you're also going to notice about topology is that the topology doesn't change, even though the geometry is changing drastically, right? You're getting very, very different objects. But the topology itself, what is connected to what, continues to be exactly the same. So when we were dealing with Topologic, we looked at sort of, okay, where are we in kind of BIM systems? What do we do, or CAD systems, or modeling, 3D modeling systems? Obviously, everybody has a layer of numbers and maths, or zeros and ones and numbers and all of that. That's absolutely fine. We all have it. Then there's a layer on top of that, which is geometry, right? Which is where things are located, their shape, etc. Then you have to put on top of that a layer of topology. And that's where we start diverting from BIM systems, because BIM systems sometimes have topology, sometimes they don't. Sometimes it's ad hoc. Sometimes, let's say, you can ask a door what two rooms you are in between, and that's topology. But then if you want to ask a room, okay, what's above you or what's below you? You know, am I a library and on top of me is there a dance floor? It cannot tell you that question easily. So you end up writing ad hoc methods in order to answer these questions. You hard code them in, or you write a little kind of plugin or something to make up for a weakness in the overall data structure, or the class hierarchy. And on top of topology, in order for it to be interesting, you have to add a layer of semantics. You have to add some meaning to what you are doing. So I just said door between two rooms, right? So it could have been a point between two cells, or could have been anything, or a city between two other cities, or a bridge between two villages. So the semantics become really important to add. BIM is very good with semantics, actually. They have a lot of semantic information into it. Sometimes it's not well structured. Sometimes you have to dig deep to find it. But what Robert and I found really missing is this idea of topology. It's right. It's really not in the DNA of BIM systems. It's missing. So we wanted to add it. So I tweeted this image not long ago. And if we are talking about numbers and maths and geometry, you can simply say that B is closer to A than C is to A. That's very obvious. B is closer to A than C is to A. You can measure it with a ruler. That's absolutely fine. But you notice these weird dots on there, and I'll get to them, why they matter when we're talking about topology. If we're talking about topology, actually, you will understand that B is actually further away from A than C is from A. Why is that? Because there are more topological entities for you to go through to get from A to B, mainly 3 edges and 2 vertices, than to go from A to C. From A to C, I can go with 1 hop. It does not, the geometry doesn't matter. So in Topologic, an edge could be, for example, a catenary curve or a chain of some sort. But when you talk about it topologically, it is an edge that has a start vertex and an end vertex. It doesn't matter how geometrically complex it is still an edge that can separate, let's say, 2 faces, and it has an endpoint and a start point and an endpoint. Now that's topology. But if we talk about semantics, if we put a layer of semantics on top of the topology, you can start talking about other things. You can say, for example, it takes longer to get from A to B, then from A to C. And semantics can combine both geometry and topology. So if I say those dots that are between A and B, one is a construction zone, and then one is a red traffic light that takes forever to turn green, and these are roads and cars, I'm adding a whole layer of semantics. And you can imagine that somebody starting from A and going to B might take him or her longer to get to B than it is to go on a freeway and get from A to C. So semantics becomes really important to combine with topology and then with geometry as well. The other thing that we were unhappy about when it came to BIM models is that BIM software invites you to create complexity, does not really require you to be very rigorous. It requires information, but rigor and information are a bit different. And then really does not support simplicity, like the simplicity of setting out your architecture. So as architects, we knew that architects start from a very simple conceptual starting point, but with rigor. Like they know exactly what they want to do. They have that kind of map of what they want to do, but they have no way of representing it using BIM systems. And then we also know that software is really fantastic at adding complexity to a model, but not really good at simplifying complex models. So if you look at this example from Vitruvius, which is he's describing how to do this Corinthian capital, right? The description does not talk about the complexity of the leaves and all the sculpting that is required. But I can create the basic shape and the basic rules. I can follow the rules, and then I can tell software to add that complexity. And we've all seen them where you see a very complex animation, let's say a very complex object, you know that behind the scenes is a very simple polygonal model of some sort that has been imbued with a lot of instancing of objects or something else. So we can go from simplicity to complexity very easily. But if I give you this Corinthian capital and say, okay, now tell me the rules behind it, and it is just a mesh, and it's a very complex mesh, it becomes really, really difficult. There are tools that try to do that, inverse CSG and other machine learning, ways of trying to understand this and looking for features and coming up with the basic model behind it. But it is a lot more complex, and it's a challenge for us. So Topologic invites you to start simply, start with rigor, and then hopefully allow software to create the complexity for you. You don't need to do it and waste your time as a human to do it yourself. So what kind of topological relationships can we have in Topologic? We can have one which is called decompositional relationship, which you can find in other software, by the way. This is the simplest one, and you can find it in Dynamo, for example. And it can be consecutive or unconsecutive in Topologic. What does that mean? In Topologic, we have things that are like a vertex, an edge, a wire, face, shell, and cell, and the cell complex, right? Starting from a point to an edge to a wire, face, and solids, and all of that. You can ask a cell complex to give you its cells, the cells that make the cell complex, or you can ask the cell to give you its shell, or you can ask the shell to give you its face, so on and so forth. That's called, decompositional. And you can go in Topologic step by step, meaning you can step down one dimension. You go from a cell complex to a cell, from a cell to a shell, or you can skip a step, or 2 steps, or 3 steps. So I can ask the cell, just give me your vertices all in one go, and it will, or give me all your edges, and it will go. So it has kind of stepped over these things. This is the unconsecutive part. So we can go down the tree, to go down the hierarchy. So what you see here, for example, this is from Topologic on Blender, that, from this twisted model, I said, give me both the faces and the edges. So the edges are highlighted a bit in yellow, the faces are in blue, and then I kind of like explode them a little bit or move them away from the centroid. And that's how you get the decomposition of your object. That's absolutely fine. Same here. So you can, get a torus, take its faces, convert it to geometry, explode it, etc. The other way is the reverse, to go from climbing up the tree, to go hierarchical. So you can ask a vertex, what edges connect to you? What are you part of? Or you can ask a cell, what cell complexes are you part of? Or ask a face what cells you are adjoining or part of. Because everything in Topologic is spatially resolved, we don't have double faces, let's say, on top of each other. We don't have that. We only have one face. So you can ask that face, okay, what is on your left side, what's on your right side? Or an edge, what faces come at you from all sides. The other kind of topological relationship is lateral, meaning that I can, in a cell complex that, like in this building, this is a test fit building that we, with the help of Ahmed Al-Tahlawi from Germany, we converted into Topologic, then we brought it into Blender. You can ask this cell complex to select a cell at random. So in this case, we selected this corridor, which is highlighted in yellow. And then we ask this corridor, give me your adjacent cells. So there's a call in Topology that says cell.adjacent cells. And it gives you all these red cells around it, all the rooms that kind of like share faces with it. So this is lateral topology. With lateral topology, also we can have connectivity. So you don't have to just ask for the thing that is immediately adjacent, but using dual graphs, we can say, can we get from cell A to cell B? And if so, what other cells do we have to go through to get from cell A to cell B? So we can find remote adjacency. And in this case,
can I ask you a question?
Yes, please.
Yeah, so I'm considering, like, for example, if a user is modeling, let's say, a face of a building in Rhino or Revit, like the things I imagine what happens in the backend is if you have a face, you'll have all the vertices, all the edges of that face in the backend. And if I join two faces, even Rhino or Revit might have that relationship. So I'm still figuring out like what kind of like differentiation when someone is modeling faces is happening on backend in Topologic versus those software.
Yeah. It depends. It always depends on two things: the underlying engine or kernel, as we call it, and then have you written methods into its API that can answer those spatial queries. So both Rhino as well as ASM, Rhino Common as well as ASM, as well as Open Cascade that we have decided to use, they all have non-manifold topology as part of their kernel. And you can actually get that information, as you said. The problem is that people have not written all the methods in a kind of a rigorous, complete API in order to get that information. So for example, in Dynamo, I can take a solid and say, give me your faces. I can take a face and give me your edges and your vertices. But I cannot ask an edge to give me the face that it belongs to. I cannot climb up the tree. I cannot do lateral topology. Not that it cannot do it intrinsically, nobody has written it. So we decided not to write the API on top of an engine like ASM or RhinoCon, but we decided to use Open Cascade because it is open source and free, and you can move it to different software, different environments. But somebody could kind of surgically remove Open Cascade and replace it. I've been having discussions with Ian Keogh with Hyper about that. Actually, he recommended that. He said, enough with Open Cascade. It's too big. It's too complex. But it is very powerful for us. Can we use something like a very lightweight way of doing it? If you notice, Hyper, for example, now do have a little bit of topology in their software, which is fantastic. I mean, and they are able to do it. Topologic is kind of the superset. It has done everything. There's about 200 methods in it, and it just takes rigor in terms of understanding what a designer would want out of it. Like you ask for adjacencies. The kind of methods that we have written and the way we wrote them, we thought architects and designers would want to ask those questions, would want to use those methods. And then on top of that, I have written now more custom nodes, basically, like larger hyper methods or larger methods, that use a lot of the smaller API methods to do something really interesting, like space syntax stuff, like depth map and graph theory will show that. And other people are, have written some, on top of Topologic, they've written other things, and I'll show some examples.
So, like Topologic, you have considered while developing the software itself that people might query based on the edge what face it belongs to, and those functions are written which are callable. But
Yes.
in other 3D modeling software, it's not. But if they write those functions, will it be the same as Topologic if they start
I think so.
adding those methods? Okay.
Yes, absolutely, absolutely. When we were, for example, just to give you an example, when we were developing Topologic, I was doing work alone before I could bring it to the team, prototyping the functionality in FreeCAD. So FreeCAD is another piece of software, really interesting, open source, free, all of that by the name, based on Open Cascade. So the same engine. They don't have the methods that we have, but by writing Python code, I was able to create our method, prototype it basically, and say, okay, here's how we get all the vertices. Here's how we ask about adjacent. Here how we do a dual graph. All of that was written. I wrote it in Python as prototyping. Then I would bring it to the team, and we would write it in C++ for efficiency. But yes, we could have used Rhino Common. We could have used ASM. We could have used other engines. We actually published a paper comparing all the engines that we could find, both commercial, non-commercial, manifold, and non-manifold. And based on the features and capabilities, we chose Open Cascade.
And I totally understand.
Yeah. Right. So one more type of topological relationship is what we call regional. And this is having to do with non-constituent topologies. And this is another thing that you don't find in things like Dynamo and Grasshopper, which is you can associate something with something else. It's not part of it. Like, yes, it's fine to ask for the edges of a face. But if I wanted to put a window in a wall, an aperture in a face, as we call it, we would like the aperture to be part of the face. But also we would like the aperture to be part of the room, so part of the cell. So these are what we call non-constituent topologies, meaning they are not needed to build the actual topology. They're not the kind of, part and parcel of it, but they are important to have. So we have ways to add apertures and other kind of locate things that are part of another topology, but they're not a constituent member. On top of that, we decided to add the idea of graph, because we knew that what we are dealing with basically is a graph. We have the topological graph, but we also can have a semantic graph, and we can have a dual graph. So there are different types of graphs. So graphs are basically just points and lines or nodes and edges, but they explain the relationship between objects. So instead of having only an implicit graph, because when you talk about a face having edges, you can imagine in your mind that the face has a node, a single node, and then 4 nodes for the edges, and then edges that connect them. That's kind of an implicit graph. So we decided to make that explicit and visualize it as a graph, and I'll show an example of that as well. But by having a graph, we can do graph theory, we can find shortest paths, we can compute centrality, we can compute completeness or degree sequence or minimum spanning tree, etc., etc. So what you see here in the cricket, the colors are basically, there's a point that you don't see somewhere. I think it's on its head. And it's computing the topological distance from that point to all the other points on the cricket. And based on that distance, topological distance, not a metric distance, the topological distance, it's coloring the cricket. So the things that are far away, obviously the extremities are quite far, they get a dark blue, and the things that are very near, they get this kind of bright green color. So this is, for example, is a spanning tree. So I think it was an icosahedron, 12-sided, I think, or something, or dodecahedron maybe. And then created the graph of it, which means all the faces become points, and then the things that are connected becomes edges. And then we have a method that is called the minimum spanning tree, which is what is the minimum graph, minimum wire that is needed to reach all the points on that graph. And then you delete everything that is not needed, just as something you can compute, it's available. We added also some options so that, it's just not, you just don't just go from like face to face, but you might want to pass through the shared topology. You might want to connect to external edges, or you might want to connect to external apertures or shared apertures. Or you might want to go from one room to another room only if there is a door between them, only if there is an aperture between them. So we added all of these things as checkboxes, as you can see here on the right. And graph applies to all topologies, not just to cells, not just to spaces. Like this is a graph of a shell, like a cardboard box that's open. And yeah, you can do these types of things in it. So in this case, you see how I'm basically testing going to exterior apertures, going to exterior topologies, and using the internal vertex, meaning make sure the vertex is inside the cell. But all these red cubes, well, some of them are the aperture, which is the window. Some of them are a topology that's exterior. So Topologic can very easily distinguish between what is exterior, what's interior. And we use that a lot, to do external walls and internal walls. What is near and dear and really is unique, I think, is how we use semantics through dictionaries. We have dictionaries, and a lot of software has dictionaries. You can put attributes, but basically in other software, those are just simply added on. They're just an attribute. A door has a manufacturer, has a cost, has a width and the length, and opens to the left, opens to the right, whatever. That's absolutely fine. But what we did here is that the semantics, the dictionaries, both affect and are affected by the operations that we are doing. What does that mean? When I'm trying, for example, to glue two objects together, I'm trying to merge them together, I can take a look at the dictionaries and have the dictionaries affect what is going to happen at the end. Or I can also have the DNA, the dictionaries of the parents, transfer automatically into the children. A very simple example that I always use is like if you are, let's say, dealing with space programming and you have a living room and you have a kitchen space and you are bringing them into an intersection, the space in the middle that gets intersected automatically inherits the dictionaries of the two parents. And it will tell you, I am the child of a living room and a kitchen. And that means you as an architect can decide, oh, I can make that into an informal breakfast area or a dining room or whatever you want to, whatever your rule is. But it will always tell you where things came from. That means that the geometric operation is affecting the dictionaries or affecting the transfer of semantics. But also, as you will see from the work of Miguel that I will show, the semantic information affects the actual geometric operation. So if, for example, if I have a building, a cell complex, and some spaces are offices and some space is an atrium, and then I want to slice this building into floors, the atrium can say, because I am an atrium, I do not want to be sliced. I want to continue to be a continuous surface or continuous cell, from bottom to top. Just based on its dictionary, you can affect, or it can affect, the geometric operation that's taking place. This is from a previous previous presentation that I did, so you can see the graphics change a little bit. But basically, Topologic is really good at representing space. It's really good at abstracting things, and it's really good at allowing the entities that you are modeling to be aware of what's going on around them because of the topology information. So just to show you some examples for some applications. In this one, this was some time ago, a couple of months ago, even more, where Revit announced that they can do pathfinding. But I found out that they can only do pathfinding on one level. Like they will not go down the stairs, they will not go down the lifts or elevators. So I took it upon myself to take a Revit model, bring it into Topologic, build a cell complex, and combine it with both visibility graph as well as the normal dual graph that we have. Visibility graphs are two-dimensional. Our dual graphs are three-dimensional, but by combining them, you can connect that whole mesh together. And we have now a way to go to find the shortest path from one room on one level to another room on another level, going only through doors and through stairs or elevators. Like it knows about them. And even on the elevator, it will do it correctly. Like it will climb up step by step. And it's that, I mean, obviously that took some programming, but I had the infrastructure for me to actually create that. And once I had, the infrastructure, I can then ask it question like, what spaces do I go through to get from office A to where the coffee machine is? So you see it here. Yeah, go ahead, Mike.
I think this is super interesting. So I'm just still understanding like how a BIM model was brought into Topologic, and was all the relationship and semanticness being like manually assigned, or it was hard coded and
I will definitely, I'll explain that. Nothing was manually assigned. No, it wasn't done that way. It was all a big dynamo definition, basically. But we took the rooms. You know how in Revit you can have rooms, which are, we took the rooms, and then, but the rooms have gaps between them, so they're not really touching face to face. Apologies, somebody came home. They're not touching, so you can't really build a cell complex. So what we did is, the trick is to get the doors, and thankfully the doors had the topological information about which two rooms they are connected to. If you have that, then you can build a graph. You can say, okay, from this room through this door to this other room. So we build that graph. For the stairs, obviously, because they are intersecting, their space is intersecting, we could immediately have a cell complex that goes from one room to the other. So once you get into a room, you can get onto the stairs and you go up. In terms of climbing the stairs correctly, this was me kind of obsessing a little bit and saying, let me find all the horizontal faces, let me find the largest ones because those are the threads, put a point on the graph for each one of them and then connect it to the next one, sort them in the Z, so now you can climb up. It's just a bit of programming, really, obsessive programming, really, to kind of connect. But the entrance to the, what I could have just simply went from the bottom entrance to the top entrance, which because connectivity is important. But I just wanted to show that with a little bit more work, you can climb up the stairs correctly and turn on the ladder.
So when you say graph structure,
yeah.
Is it like the rooms are nodes and the relationship between the rooms are edges?
100%. So what you see it actually in the lower right corner, these blue lines, it's an actual graph. What I added is for each level, I also added a visibility graph, which allows you to go with, like turn around corners and not hit into something. Because, topologically, I can just simply go through a wall. I mean, geometrically, it doesn't care if there's an obstacle or not. So I wanted to also avoid obstacles and go correctly. So I combined a 2D visibility graph with our 3D dual graph, plus some additional edges and vertices for the staircases and the lifts, and then just connect all of that and create a big graph. Plus the rooms have semantics, so the dictionary of the room, like the room name, room ID, gets inherited into the vertex of the dual graph. Does that make sense? Like, if you said a node represents a room, why not just simply take all the dictionaries and all the attributes of the room and just copy them over and embed them into the node? That's what we do.
So like, when you say visibility graph, is it like throwing rays and finding where are the doors and openings where one could pass? So the room features knows that there is this particular angle where I could cross from one room to another.
Yeah, a visibility graph basically, like connects every point to every other point, removes all the obstacles and reduces the graph so that you can find the shortest path, through an obstacle. Like it will go to the edges of an obstacle and then back in. It's a very simple method. You can find open source software that does that. Dynamo has a very nice visibility graph custom node as well. It just, as you can see here, it kind of like creates a mesh, but but actually gets around any obstacles and turns corners. It's what you can see from what point, basically. That's what a visibility graph is.
And I sorry,
No,
I'm just understanding, like, you have like a Rhino, like, sorry, a Revit building. So how, like, the cell complex, like, is defined, because it might not inherit from Revit. So
if we a lot of the questions I get is, can we go from Revit to a cell complex in Dynamo in Topologic? It's not always feasible. What we found is that I always say that Revit is actually more 2D than 3D. It's a 2D piece of software, and I hope I'm not insulting anybody. That Revit is obviously a fantastic piece of software and very successful. But why do I say it's 2D? It's because a lot of the topological relationships are much easier to do in 2 dimensions in a floor plan. So if I get the rooms of a floor plan and I get the center lines of the walls, all these rooms will touch, and I can build a cell complex, and therefore I can build a graph. Because if they're all, and I can remove, I can, obviously Topologic removes all the duplicate faces by itself. So I can get a really nice cell complex out of a 2D of a single level. The problem becomes when you're talking about the floor above you, because they do not get you the same, they don't treat it the same way. So you have a gap. And then it becomes a problem of, like, how do you match and all of that. As I said, in this particular example, we did not even have to build a cell complex. What we did is we immediately went from the rooms, whether they're connected or not, the cells, made cells out of them, and used the door information to connect the graph, to create a graph connection. So 2 rooms, 2 cells that even they are not sharing a face, and I cannot build a cell complex and I cannot build a graph automatically, just because I knew that there is a door that connects room A, ID A to ID B, I simply manually through software, but sort of, just add an edge between those 2 rooms, because Revit had that topological information. But this is what I call ad hoc topology in Revit, in that in this case, we were lucky and the doors had that information. Actually, it's an option. Doors don't have to have that information. You have to actually go down 3-4 steps in Revit and click and say, I want the door to have that topology information. But there is nothing in Revit that says, I want to make sure that the room above me is kind of connected and knows about what is below it. It doesn't know that. You have to write ad hoc software to do that.
I see. So because there is a graph structure, there are features which can say this floor is geolocated here, and there is this semantic information of second floor to first floor connection, and that is not easily accessible or not there in other software.
Yeah,
and the
exactly.
graph is connected, so I can use that connectivity feature to find the shortest part between floors, not even one floor, but multiple floors.
Yes. So we decided that, the way we did it here is that we're not going to worry about rooms above each other, because usually there is a slab between them. Therefore, you're not going to be able to travel. But we used the cells of the staircases and the lifts to connect. So it naturally only goes through staircases and lifts, which is exactly what you wanted. But if the model, for some reason, for example, had an opening and had just simply a ladder of some sort, let's say, or a mezzanine or something, and some steps that were not really staircases, we wouldn't have recognized those. So I think there is software that needs to be written to actually look at a Revit model and look at the geometry, look at the location of things and the semantics, and then build a fully topological model out of it. The information is all there. Behind the scenes, it's a graph. As I said in one of the other presentations, a building is a graph. The question is, can I have access to that graph? Is it explicit? Is it all connected? Do I have all the topological information and the semantic information? If we represent a building as a graph from the beginning, a lot of problems will be solved automatically for us. But right now, it is a hybrid between a graph and a building database and some random attributes thrown here and there and geometry. And it's just a lot of complexity. what we are hoping Topologic will do, if nobody even uses it, it will instill the idea that start with a graph, start simply, build a very rigorous interconnected graph, and then let the software add the actual building fabric and all the complexity that you need and put all the chairs in the conference room. Well, you don't need to do that, obviously, but just have a building that is well connected from the get-go.
I think like I pretty much got like a good level of understanding. Like I think it's a very smart approach to start with a graph with all the features. So when the model gets more complex, you could use those relationships and get valuable data out of it.
Yeah, and it will also enable a fast iteration, which is now, despite all the promises of BIM, once you get to this level of complexity of walls and doors, it's not easy to change. But if I have this kind of like what I call like almost like a, they call them a control surface, right? We have control surfaces. You can change the control surface, and then the wall and the detail on the connection and the layering of the walls and the bricks and all of that will all kind of repopulate and recompute itself. But you don't want to be changing complexity. You don't want to be dealing with complexity. You want to deal with your control surfaces.
Yeah.
So just to very quickly, I know we're just running out of time a little bit, so I just want to show some examples. These are very old examples. We used it for multi-objective optimization with what is now called generative design. It was called Project Refinery. But again, because it was linked to Energy Plus through Open Studio, we were able to do very quick iterations on that. This is the same. This is where we were optimizing total glazing area and average cooling loads, very, very simple things. We used it with fire simulation. So we connected it with Dynamo. We connected it to something called FDS. So we were able to use a cell complex and define the apertures as doors. And therefore, we could tell where the smoke is going to go. So this model that you see in the lower left corner was derived from this kind of simple cell complex in Dynamo. And then the temperatures and all of that will follow through. We didn't stop there. We also combined it with a branch of machine learning called reinforcement learning, in which we allowed an agent to learn how to find the escape routes while the fire is spreading. So we got the information back from FDS about how the fire is spreading. Those are the red spheres. And this yellow agent, this yellow cone, is trying to find its way and learning how to find the fire exits. And the idea here is that by placing those fire exits, those green spheres, in different locations and observing how this agent is trying to learn, you can perhaps get an insight whether you place them at the right place or not. So regardless of the minimum distances and the regulations, can this agent, which is a very dumb agent, it takes 1,000 iterations to learn or whatever it is. But if it learns faster, that means you have made the job easier on it, right? So you can play what if scenarios. It's not a simulation of how people will evacuate a building. It's really at the front end for designers to say, did I place these fire exits in a reasonable location? So we did that also on a Revit model as well. So in this case, we started the fire on the second floor, as you can see where the big red circles are, big spheres, and the agent is this purple cylinder. And it learned to kind of duck down and find those green exits at the bottom. We put some exits at the top and some exits at the bottom. It does not have a goal to reach those exits from the beginning. That's not how reinforcement learning works. Basically, you just reward it or punish it based on the move it made. And just by this kind of reward system, it builds a decision tree, a decision kind of table that allows it later on to have a goal of getting to those green, despite the fact that it might be punished on the way, but kind of like the total reward system works in its favor. It's just part of machine learning. I worked with Mikhail Digunziak early on. He took Topologic. It's now part of something called SAM, which kind of like glue software that connects energy analysis. That does a lot of interesting things, but Topologic is part of SAM. So here is like the GBX Bell model that can get created. They use Topologic as a kind of way to clean up all the surfaces and create proper spaces. I worked with Ahmed. I'm continuing to work with Ahmed Al-Tahlawi from Germany, from Ipro Consult or Ipro Consult. The main project we worked on is taking test fit models and creating topologic models so we can actually analyze them and then also move them to Revit. So it's not just a translator, but actually we can tell it, we can ask it for the exterior faces, interior faces, find shortest paths and all of that. I'll skip that one just because of time, but please take a look at it. He has done some really, really interesting things with Topologic. He tweets about them, so please check those out. And then Miguel is doing his PhD. He and I have become friends. He used Topologic as part of his dissertation, where again, he's interested in information, in what he called informational architecture. And it is, again, this idea of based on what the information is in a space, it kind of determines the fate of what happens to this object at the end. And by moving these spaces around, geometry becomes almost irrelevant for him because it is all about topology and about semantics. And therefore, if you say this is a courtyard, all of a sudden, a whole cascade of things happen because this is a courtyard now. And if you change it into a living room, some other things can happen. It's all driven by semantics and by graphs and by topology. And last but not least is Bruno Possel's work. He has created something called Homemaker that uses now Topologic. Homemaker was using a different system at the beginning, and more ad hoc, and then when he saw Topologic, he thought, oh, that's really, really good to use. So this is again in Blender. And again, as you see in the upper left corner, as a designer, that's what you would design. A simple cube, simple space, surfaces in space, intersecting, and just based on that set of surfaces, you create a cell complex that then gives you a lot of topological information. And based on that, he changes all of that into smart IFC objects. All the windows are detailed, the parapets, railings, all of that. And you can then create that type of really realistic architecture, whether you like it or not, whether it's part of your style you like or not. This can all be interchanged. But the idea is that he could go back to that very simple model and just simply change the level of a surface or change the size of it. And all that complexity of IFC gets regenerated immediately. Yeah, that's all I have. I'm happy to, we don't have a lot of time, but I'm happy to just show you very, very quickly the status of it in Blender, because that's the thing that I am most excited about. Sorry about that. So yeah, this is the Cricut. And I just want to show you behind the scenes how do you get those colors. So basically, notice that these are surfaces. What you're going to see next is like a wireframe, but the wireframe is not the wireframe that you see here. It is the dual graph where a surface becomes a point and the connection between two surfaces become an edge. So I'm just going to hide the Cricut and then show you the dual graph of the Cricut. So every point that you see here highlighted in yellow is the kind of like, let's say, the centroid or center of mass of the original triangle. And then the edges connect surfaces that share edges together. And based on that, you can compute your topological distance from one point to all the other points. And based on that, you can color it, on a colored ramp of some sort. So I have you see the color ramp right here. So basically, yeah, you can take, just to kind of go through it very quickly, you take a B-wrap, or I could have brought it from Blender itself. You create a graph by that topology, you feed it the topology. I just chose the simplest one, which is just direct through all the stuff. Then I got the faces of it, so subtopologies. This is that hierarchical kind of subtopology, so you can choose what you would like to get. So it has 3,034 faces. We found the nearest vertex out of the graph so that we can start doing the computation. And then we calculate the topological distance from one vertex that we chose to all the other vertices. We found then the maximum topological distance. So it's 62 steps that you can go from one place, you can get to any other place with 62 steps. And based on that, we calculate the topological distance of each one, and we use that to create a color. And we go through that. I think this is one way of it, and then I just did it the other way with a color ramp using the built-in method rather than my own method. But that's about it. Yeah, that's all I have for today. Right on time, I think.
Yeah, this is so incredible work, and like I think I'll start debugging and going like what's going on with each component, because this is super interesting, and especially with the examples of reinforcement learning and graph structure. I think there are a lot of amazing developments which can be built using this semantic and topological information, which is like required for like BIM AI models. So
yeah, so one thing that I have not talked about is all our work with AI and machine learning. So we've already published a couple of papers. I mean, obviously reinforcement learning was published at, I believe it was EKD a couple of years ago. We now have a PhD student working on graph machine learning that is understanding, classifying buildings and their relationship to the ground based on their topology. So he's generating the data set and training a neural network on it. Yeah, we have a few things that we are doing with AI and Topologic. Once you have graphs, you can do a lot of work with graph machine learning, definitely.
I know. Sorry, go ahead, Richa.
Yeah, hi, Mrs. Zavi, and hi, Mayur. So I was just wondering, this 3D pathfinding was really, really interesting. The way it is, we can detect the smoke going and everything. I have a small question, like, can it be not going through the doors? Can we add some intangible features like if, for example, if we use for healthcare functional building, so like for example we are using OT at some time of duration, and the other places like maybe the waiting area, so that we can find the relations between them and find the graphs of it, and then we can design our building further on the typology of the usage. Can this be done here?
Yes, absolutely. It's actually a student of mine in the master's studio, in the MArch studio unit, was designing a vertical hospital. And he used Topologic to do a study on kind of separations and zones and how you can, I think he used it for infection control, if I remember correctly, so that you could find what can be connected to what shouldn't be connected to what. I've had Topologic be used for generating elementary schools, for example, starting from a building program, generating the graph, and then trying from a graph to generate an actual floor plan that satisfies the topological requirements of the original building program. All of these things are definitely possible. You have to think of Topologic as a foundation. It's not the whole building, it's the foundation of the building. And what you need to do is write domain-specific software on top of it, or create very complex Grasshopper or Dynamo or Blender, Spherechalk workflows on top of it. But now that it's available in Python, it should be easy or easier to write new software that calls it as a library.
Thank you, Mrs. Zabi. It was really nice.
Thank you. Thanks for attending.
I know we have limited time, but I'll keep my questions to a few. So I know you are involved with a lot of things. Like I got to know your collaboration with Theo on blockchain. You are attending like conference work. So how do you manage time and like so many research work?
Sleep is overrated, first of all. But more seriously, I am in a very privileged position because being an academic means that you have a day job and you have a source of, I'm not doing a startup, right? I'm not, chasing funding, or at least I am chasing funding, but if I don't get it, I still get paid, right? So this kind of stuff is expected from academia, right? You're expected to conduct research. Now, if we were privileged to have 3 years and 300,000 pounds to spend on it. So a lot of this work was happening because of the Leverhulme Trust funding. Now that has ended. It's actually ended in 2019. And I've used this kind of momentum to continue working on it. And I knew that it will die if I don't make it open source and bring it to Python and to Blender and to all the other tools. So this is what I'm doing right now. It will run out of steam if we don't get our next round of funding in maybe in a year or so. So I'm always looking for support to do it. Beyond that, it's for me a way to stay engaged and to contribute. So there are people who are using it. I think in academia we have something called impact, and impact is impact on industry. So my main mission right now, beyond the research, is to make sure that Topologic, whether the software itself or the idea behind it, has an impact. Infects in a good way, not in a bad way, infects how people do design, and they start thinking of a different way of doing design. But other than that, I'm just dedicated to it. It's my pet project, so I work on it day and night. Yeah.
Yeah, I can only imagine the hard work behind this. And like, to be honest, I felt the same analogy when like Elon Musk gave, like, even if Tesla doesn't become successful in the electric vehicle market and other competitors beat them, like the idea of promoting that phenomena is so strong. So even if like other companies adopt this, like the foundation has been built and it's gonna benefit the whole industry.
Yeah, no, absolutely. I mean, like, I'll give you an example. When Hyper tweets about, like, they've done a cell complex or topology, some people would say, oh, Topologic does that. Is that using Topologic or something? And there's a lot of sensitivity about that, of course. I feel actually it's absolutely amazing that if they can actually take all these ideas, I know they have done work on their own, actually, and I've kind of talked to them about it. But even if somebody comes in and says, "Oh, I love topology. I'm going to just kind of create a whole system based on in Unity or some other engine, and just design all of that, or I'm going to add it into Revit," our mission would be accomplished. We want that kind of thinking to start becoming part of the mainstream. I don't care if it is Topologic. I would love for it to be Topologic or an improved version of Topologic. But if it's something else, but that uses the ideas, so be it. Yeah.
And apart from Topologic, what are some ideas or research questions which makes you excited and you look forward to the next morning?
The other research that I am working on is large-scale robotic fabrication of sustainable material. It has nothing to do with Topologic, but we have a nice large KUKA robotic arm. It can do 2 meters and 60 kilograms. And we have designed a bespoke dual extruder for it with Mogama, who's now in Australia. And we are 3D printing cob, which is a sustainable material. It's basically mud, earth, and straw. And so, but once you 3D print it, you can get some really interesting results, both from a performance point of view as well as geometry. So other than kind of this type of work, it's really almost the other spectrum, which is physical 3D printing of solid objects.
Yeah. And was there any low point while developing this software that you felt, okay, it's gonna be either go all the way in or it might go nowhere?
Oh, there were many low points, and there were many discussions with Robert and Simon and the whole team about how things. We would argue about the naming of methods. We would argue, Nicholas would implement something, and we would look at it and say, like, that's not how we're gonna do it. Like, for example, right now it works very magically in the sense that you can just get any cell and then ask it what cell complex you are part of, or, you know, whether you're adjacent cell, without giving it any kind of information. You just ask it. Before it was, we would give it the kind of the grandparent of it, you know, and that looked fake. That looked like, oh, well, yeah, of course, if I have the grandparent, I can kind of step down and find the cell and its adjacent cells. But right now, you don't have to do that. So we did a lot of work behind the scenes. In many cases, the thing that we thought was not going to work was the translation between the built-in geometry in Dynamo and the built-in geometry in Grasshopper to Topologic. And I'm really happy to. This was actually took more work than Topologic itself. Is the translation from like all the NURB surfaces in Blender? It's all unfortunately so far it's all flat surfaces, right? Planar stuff, you know, just meshes. In Dynamo and Grasshopper, you can deal with any kind of NURBS curvature, etc. It will translate it correctly. So just getting that to work took a couple of months actually, because we did not know the data structure, and the documentation on it was not very good. But in Dynamo and Grasshopper, you can go from NURB surfaces into Topologic and out into NURB surfaces again with almost no loss of information. Like you can get the geometry exactly as you inputted it in, which was a big accomplishment, and we thought we'd never get it. We were going to revert back to just planar meshes like we do in Blender right now. I have not yet figured out how to read NURBS. But Blender is not very good with NURBS anyway. I mean, it's all based on subdivisions and planar meshes. So we decided 99.9% of architecture is straight faces, so it's okay for now.
Got it. And I want to get this clear before, because that will stay in my mind for a long time. So the way I understood, like surface level, I got pretty good understanding of the whole software, but I want to see like how behind the scene stuff works. So if let's say this is a living room, this is bedroom, this is another room, and there are connectivity between each, like let's say this indicates there is door. Will like each room has like features, okay, 4 faces with 16 vertices, and all those coordinates are like stored as like number or features, like okay, 1 2 3 4 are the vertices.
We store full geometry. So, you know, we have the cell class, but the cell class will have all the faces, all the wires, all the shells, all the edges, all the vertices. And you can go all the way down to asking the XYZ of a vertex, but also edges, because as I said, in Dynamo and Grasshopper, an edge could be like a curve. So you can get the geometry. We do not throw away the geometry. So all that is stored in something called OCCT shape. So underneath, you know, we're using Open Cascade, which is a full 3D kernel. So everything is based on geometry, obviously. But on top of that geometry, there's also topology. But yes, it is fully three-dimensional engine, and we do some geometric operations, like figuring out the volume of a cell, slicing, dividing, you know, unioning two things, finding the intersection of two things, finding whether a point is inside a cell or outside a cell, or inside a face or outside a face, or finding the midpoint of a point or a line, excuse me. Yeah, all that geometry is available, definitely.
Yeah. And like what kind of contributions are you looking forward? Like if there are people who are interested to do some open source work or collaborate with Topologic, what are some areas they can look into?
I think that, I mean, obviously the source is available. So anybody who is who knows C++ can take a look at the horrible work, all the cobwebs that we have in there, and maybe do pull requests and say, clean that up, it's wrong, you know, whatever. Because, you know, like every software, I can crash this in 2 seconds if I wanted to. I mean, there's always that thing. But the main thing really is what we're missing right now is the ability to transfer all sorts of geometry in Blender, including NURBS, to Topologic and back out. Because I would like equivalency between Blender and Dynamo and Grasshopper. I don't want the open source solution to be in any way less than the other solutions. But mainly, I would like to see people use it. Like I would like people to see people, see people put other layers, domain-specific work on it. So I'm very excited when Mikhail Dogunziak, for example, incorporates it in SAM, or when Ahmed uses it to find out the rentable area in Revit, because he can do topologic analysis and automatically assign apartments out of a soup of rooms. He can immediately tell you which rooms belong to the same apartment, and then can categorize Revit into apartments, and then can tell you the rentable area. Something mundane as that, or what Miguel does with his dissertation. I would like to see people kind of applying it in some way.
And last two questions I have. Based on your learnings in software development journey, what's your piece of advice to computational designers who are interested to learn software development?
Practice, practice, practice. It took me, what am I now? Oh gosh, 35 years. And I consider myself an amateur programmer, and I know only up to a certain level. Not a full stack developer. I don't know C++ very well. It's my Achilles heel. I'm not very comfortable with it. I started with Fortran, and then Basic, and then Objective-C. At a certain point, I was developing stuff for Next, for the Next OS, and then Python. But in the MSc that I teach here at Cardiff University, one required module is Introduction to Python, and the second required module is Algorithmic Thinking with Me, that also uses Python and Dynamo and other places. So it is an absolute requirement that they will graduate knowing Python very well. So it's not enough for me is to use tools. A lot of people use tools, and there are some wonderful, wonderful tools and plugins that you can download. Grasshopper has a huge ecosystem of that. But it's at a different level if you start sharpening and making your own tools. Either sharpen another tool, take another tool and hack it and modify it. That's absolutely fine. Or start something from scratch. And it's a completely different world when you are able to do that.
And like, it's quite interesting that you have like a special module focused on that. So based on your experience, like, what are some gaps you find between academia and industry? And like you are also the course director, so how do you ensure that the students are well prepared for the professional world?
Yeah, I mean, the main gap is that is a lack of understanding. So in this, the old guards, I call it, so like the big companies, etc., even if they have a geometric or computational unit, or they're doing some amazing things with BIM, etc., it's not taking them to the next level of enabling efficiencies and collaboration. They're just automating things, or they are making sure their standards are working and the work is at a certain quality, etc. That's good for them, but it's not pushing the field forward. Then you have the startups and the new generation, and they are all doing amazing things, but they are not of the scale and the impact yet to make a change. My responsibility as an academic is to show my students both worlds and say, you might end up operating in one world, but what you really need to do is start, again, in a good way, infect that process with these ideas that we are seeing coming out of the startups. Otherwise, nothing is ever going to change. Or if you are brave enough and you have the resources and you can do it, either do your own startup, and I have a student who was doing their own startup, or join a startup, or join a really innovative company. So my duty as a teacher is to point those out and to give them the equipment and the tools they need. And to me, the main thing I can contribute from my own little world is to say, here's some ways you can build your own tools, or at least take something and hack it. Don't be scared to do that. So like that's the way to move things forward. Once they see that how easy it is sometimes to hack something, change it, then the door opens, and then hopefully they will be able to build innovative tools and change our industry. Our industry is is in dire shape. I mean, we are so behind. When I look at you as well, I mean, I've seen your interviews, I've seen what you're interested in. We are always looking at what's going on in other fields, right? And saying, look how amazing they're doing this here, and we would love to bring them, and some people bring them back into architecture. But I would love to say, look at this amazing innovation in architecture, and maybe aerospace industry would learn from us, or maybe nanotechnology would learn from us. You know, and there are very few examples of companies that are doing at least something interesting.
Professor Jabi, you hit the spot. I always feel bad and skeptical when people say AEC is innovating, and when in the name of innovation they are doing cross-disciplinary tech integration, and what is the core thing which other industries are adopting. And I wish in the goal in next couple of decades we develop something so that the whole the world can learn from it.
I hope so too.
Yeah. Okay. I have questions, but I don't want to keep you late, so I'll keep it optional. Either can you answer what things frustrates you the most about AEC, or is there anything you wish you would have done differently in your career?
Oh, the last one will take forever. Will take another couple of hours for me to answer, because I have a lot of things I wish I had done differently in my career. But I mean, I don't want to dwell on anything negative. I don't want to end this on a negative thing with frustration in the AEC. I think it is. I'd like to look at the amazing potential for AEC industry that is out there. And some of it is kind of, we need to go a bit, vertical and deep and do innovation. But a lot of it is also maybe integration work between these innovations. So we have people doing machine learning. We have people doing computer vision. We have people doing amazing fabrication stuff. We have people like me doing topologic stuff. I wish somebody would come in and say, oh, look, I can combine this with that, and A, B, and C, and put them together and create like a really innovative process. So sometimes it's about, the common thing we always say is like, enough with the pavilions, right? We've done so many pavilions year after year after year, and it's fantastic. But we want to move beyond that. I think the industry is hungry for saying, can we please put plumbing and the electricity and the reinforcement in the 3D printed concrete? And can we finally figure it out? Can somebody sit down and do maybe not very interesting work, or maybe not very innovative vertical work, but really innovative integration work? But can we move it to the next level? And that's what I wait for. This stuff excites me more than somebody doing like a really fantastic little toy piece of software, which could be very innovative. But I feel like, are you going to keep working on it, or in 2 months, 3 months, I'll see another innovative piece of software, but this one was left in the dust? I see a lot of innovation that kind of like it starts and stops, and I don't see the integration happening.
And why do you think it's not sustaining, or it's stopping?
It's hard work. It takes about 20 years for an innovation to kind of become mainstream, and takes a lot of money, and it takes big players, unfortunately, to adopt it. You will have these amazing pieces of software, for example, or hardware even, that never see kind of mass adoption until Apple or Microsoft takes them over and markets them. And all of a sudden, just because of Apple, we all carry AirTags now. Well, we had TARs, we had other things, but they never caught on because they did not have the support, and they don't have the kind of mainstream weight behind them. So we need these large companies. Either they will change and help us, or they need to move out of the way somehow. But I'm not optimistic that they will move out of the way. Why would they? And they're really difficult to move out of the way. Sorry,
Awesome.
I'm not politically correct here, but I'm an academic. I'm not an industry, so I have the freedom to say what I want.
Yeah, I must say I can continue on and on, but we need to end this. It has been an amazing discussion, and I'm definitely gonna test it and share something on Twitter soon about like what are some use cases I found for this, because this has been like amazing foundation, and I feel I have seen very less people doing like cutting edge work, and like this is one of the piece. So I think I feel if we can get more and more awareness about this among the community and more people experimenting, it can lead to some amazing workflows and innovation.
I hope so. I hope so. Thanks again, Mayur. Thanks for everything.
Thank you. Have a nice rest of your day.
Thanks, you
Bye-bye.
too. Bye, everyone.
Bye. Thank you, everyone.